Picture trying to fill a narrow glass funnel by hitting it with a tidal wave of steel spheres. You have a massive volume of material, but because the delivery mechanism isn't calibrated to the target, most of it spills over the edges. This is the trap at the base of most flawed survey designs. Researchers often assume that collecting a massive amount of data automatically yields accurate results. But acquiring a huge sample size guarantees nothing if you haven't correctly defined or accurately accessed the target group. This diagram shows the true scale of a research target. This outer ring represents the population, the complete theoretical group of people, events, or things of interest that a researcher actually wants to investigate. Inside that is the sampling frame. This is the physical representation, or the actual list you use to reach that population. Think of a company payroll or a university registry. The sample is the specific subset of dots drawn from that frame to be studied. Every individual dot within that sample is an element. Notice the physical mismatch where the sampling frame doesn't overlap with the population. This is coverage error. It happens when your list is out of date or incomplete, meaning certain elements of your target population have absolutely zero chance of being studied. What researchers are actually looking for is the parameter, the true objective mathematical characteristic of the entire population, like the actual average income of a city or the true failure rate of a manufactured part. A persistent misconception in data collection is that simply pushing your sample size, your N, higher and higher will automatically capture that true parameter. Consider a convenient sample of 5,000 respondents pulled from a single internet poll, compared to a disproportionate stratified random sample of just 150 respondents. The internet poll has 5,000 data points, but it suffers from severe selection bias. It only captures people who happen to visit that specific site and have the time to click through a survey. You have high volume, but you are reliably measuring the wrong group. The sample of 150 is carefully structured to draw specific proportions of data from isolated subgroups within the exact target population. Every data point is mathematically anchored to the real-world demographics. A sample's validity is dictated by two independent axes: the structural integrity of its design and the mathematical boundaries of its size. Volume can never outscale bad architecture. Sampling architecture splits into two distinct categories: probability and non-probability design. If your goal is to generalize your findings to an entire population with mathematical certainty, you must use a probability design. This requires that every element in the population has a known, non-zero chance of being selected. This grid visualizes the baseline method, simple random sampling, where every dot has an equal randomized chance of selection. But this has a structural vulnerability. If you have distinct but numerically small subgroups, a purely random poll can easily miss them entirely. To capture that subgroup variance, we use stratified random sampling. We sort the population into mutually exclusive, meaningful segments. The strict rule here is that there must be homogeneity within the groups, meaning the elements inside each band share similar traits, and heterogeneity between the bands. Once the strata are set, we draw a representative percentage of dots from every single band to form the final sample. If you are surveying a corporation, stratifying by job level ensures that the responses of 500 entry-level clerks don't statistically drown out the data from the 10 top-level executives. Now look at a different geometric approach: cluster sampling. The target population is sliced into natural aggregates, like city blocks. You achieve massive reductions in time and capital by randomly selecting a few blocks and surveying every single element inside them. The strict condition for clustering is the exact inverse of stratification. You need heterogeneity within the groups, a good mix of traits inside each block, but homogeneity between the groups, meaning one block is roughly similar to the next. If those natural clusters lack internal diversity, you expose the research to severe intercluster bias. You are balancing two inverse models. Stratification offers high statistical efficiency and detailed data, but costs more to organize. Clustering keeps costs low, but sacrifices efficiency. Selecting the optimal sampling frame geometry acts as a filter. Without it, you collect highly precise estimates of the wrong parameters. This distribution curve reveals the mathematical limitation of the sample mean. Your calculated average, x bar, is only a single point estimate of the true population mean. Because a single point estimate provides no measure of possible error, we construct an interval estimate around it. Precision is defined mathematically as the exactitude of the estimate, visualized as the interval width surrounding that center point. Confidence is the statistical certainty, typically 95%, that the true population parameter actually resides inside that shaded interval. The engine linking precision, confidence, and sample size is the standard error equation. Let's apply this. A bank manager predicting monthly withdrawals requires an interval of plus or minus $500 at a 95% confidence level, knowing the population variance is $3,500. Running those requirements through the interval estimation formula yields a required sample size of exactly 188 clients. What happens if that manager demands 99% confidence instead of 95%? Look at these overlapping curves. An increase in confidence forces a wider, less precise interval if the sample size remains static. To maintain that strict plus or minus $500 precision while boosting the confidence level to 99%, the sample size must bear the mathematical burden. The required sample size jumps drastically from 188 to 325. Within statistical interval estimation, precision and confidence are locked in a zero-sum game. You have to calculate a larger sample size to break the deadlock. If increasing the sample size consistently reduces standard error, it seems logical to secure a massive sample of 10,000 subjects for every study. There is a practical ceiling. Past 500 elements, standard error shrinks so far the model becomes hypersensitive. It flags tiny correlations, like 0.10, as statistically significant, explaining under 1% of variance. This creates a gap, accepting mathematically true, but practically meaningless real-world relationships. A finding can be statistically significant on paper, but holds zero utility for making a high-stakes business decision. This matrix outlines the sequence of valid research architecture. First, map the geometric design, probability versus non-probability, to secure the required generalizability. Second, lock in the standard error formulas to balance the precision-confidence trade-off without overpowering the study into false positives. True analytical rigor relies on the precision engineering of the sample's structural framework. Intentional limits are vastly more powerful than brute force volume.